After having completed the 2 units on machines, that is mechanics, including force, machines and work and energy, and the second unit on light, today we find ourselves in this third new unit, that is on sound and vibrations. Although there is only one chapter in this unit, but it is an important one because every year at least 10 to 12 marks of questions are asked from this one. So let us start with sound. So you have a basic idea about sound. Well, what is sound? Well, it is any kind of vibrations. So sound is basically vibrations. So whenever it's traveling through a medium, it can be the surface of a water, or it can be through a solid block. Basically, if the disturbance is able to vibrate this, either in case of solid the molecules constituting it, in case of liquid the molecules constituting the liquid, the particles constituting that, if they can be vibrated, if the disturbance is successful in vibrating them, then we say that yes, a sound is being produced or sound is traveling. Now this kind of vibrations, as you know, it can happen in two manners. There can be something called transverse vibrations, and something known as longitudinal vibrations. Sound can travel either as transverse waves or it can travel as longitudinal waves. Now, how do we differentiate between these two? Well, first of all, if the sound wave, that is the disturbance, sound wave is basically a disturbance of the medium particles. If it is traveling like this in kind of a sinusoidal fashion, having crests and troughs, it's traveling in the manner of crests and troughs. Crests are this topmost point at the maximum displacement from the mean position in the positive side, and troughs at the maximum displacement from the mean position in the negative side, and this is the axis of amplitude, and this is as the particle is vibrating. Now if it is traveling like this in the form of crests and troughs, what's happening is that the wave is getting transmitted in this direction from left to right, but the particle mediums constituting the disturbance, or in this case the medium through which the sound wave is traveling, they vibrate top and down like this. So the particles vibrate like this and the sound travels in this direction. So particles are getting vibrated like this, and as they are getting vibrated like this, the sound is traveling in this direction. So you find that the direction of propagation of sound and the direction in which the medium particles are vibrating, they are perpendicular to each other. This kind of wave formations are called transverse waves. And then, as I said, there is a second type, which is the longitudinal case. In the longitudinal cases, the sound travel in the form of compressions and rarefactions. These areas, these are the compressions, and these areas, these are the rarefactions. These are the compressions and these are the rarefactions. And whenever sound travels in the form of longitudinal waves, what happens? Sound is traveling in this direction, and the medium particles, whatever medium it is, they are vibrating like this, left and right about their mean position. So if this is a medium particle, it is vibrating like this, and the sound is also traveling in that direction. So as the medium particle is vibrating left and right, the sound wave is also traveling. This kind of wave motion is called longitudinal waves. So sound can travel in the form of transverse waves, also in the form of longitudinal wave. The best thing to remember is, if sound is propagating like this, transverse waves will make the medium particles vibrate up and down, and if sound is propagating like this in this direction, longitudinal waves will make it vibrate like this, left and right. So in this case the vibration will be in the same direction as propagation, and in this case the vibration will be perpendicular to the direction of propagation. Contrary to light, light can transmit from one place to another only in the form of transverse waves, but sound can travel in the form of transverse waves as well as longitudinal waves. And you probably know this, the longitudinal waves, they can travel through solid, liquid as well as gases, whereas transverse waves can travel only through solids and the surface of liquids. So longitudinal waves can travel through solid, liquid and gas, while transverse waves can travel only through solids and surface of liquids. Compare this with that of the light. Light is a transverse wave, and well, we know it can travel through any media. It can also travel in the absence of media. Now, what is the basic difference between sound and light waves? Well, sound waves are essentially due to disturbance of the medium particles. So if I have a medium, it may be solid, liquid or gas, and the sound is propagating through that medium. When the particles of that medium are disturbed, when they vibrate, sound is produced. Whereas if you look at light wave, or for that matter any kind of electromagnetic wave, is generated due to periodic changes in the vibrations of electric and magnetic fields. So suppose these are my three mutually perpendicular axes, the x-axis, the y-axis and the z-axis. Suppose this direction constitutes the electric field, and along the x-axis I have, suppose, the magnetic field. Then light will propagate along the z-axis in the form of electromagnetic wave. Light is produced by periodic changes in the vibrations of electric and magnetic field, and light always travels in a direction which is mutually perpendicular to both the electric field as well as the magnetic field. We are also familiar with this idea that whenever sound travels through any media which has got certain elasticity and density, the general formula for the velocity of the sound wave is root over of elasticity by density. Now you have studied in class 9 that this is the most primitive formula. After this, Newton provided a correction to the formula, then Laplace provided a correction to the formula, due to which the final formula of velocity was something like gamma p by rho, where gamma was a factor of Laplace's correction, the ratio specific heat to at constant pressure to specific heat at constant volume. P was the pressure and rho was the density of the medium. So that was the basic formula for the velocity of sound wave. And what about formula about the velocity of light? Velocity of light is equal to frequency into lambda, that's frequency into wavelength. That's the formula for the velocity of a electromagnetic wave. Now, once we are familiar with this basic idea, we can now delve into depth in the case of sound. Now, one of the things that we need to know is that why do we hear sound? What is the reason that we hear sound? Well, that I am speaking right now, what I am doing is I am creating vibrations in the air molecules around me. Those particles of the air, they are getting disturbed. They are moving about their mean position, either in the top-down manner or in the left-right manner. And in the form of those waves, when those waves are reaching my eardrum, the sensation of sound is produced. Now this thing that we are hearing in our ears, the persistence of hearing is 0.1 second. What does this mean? This means like if you make me hear two sounds within 0.1 second, I will not be able to distinguish them as two separate sounds. In order for me or for any human being to distinguish between two sounds as two separate sounds, they have to enter the ear at least after a time interval of 0.1 second. If the sounds reach the ear within 0.1 second, that is the persistence of hearing of the human ear, we cannot distinguish it at two separate sounds. Now if you go in certain places like in the hilly areas or in some long room, a room where the walls are pretty far, and there you stand and you shout something, you find that initially once you hear the sound, whatever you say, and then after some time has passed, you again hear the sound. This action of again hearing is what we call echo. So first, when we produce the sound is emitted from our mouth and it reaches our ear. That's the first sound we hear. And the second sound, which is called echo, is being heard when it gets reflected on a surface and comes back and falls on our ear. So this is the principle of echo. It basically varies or depends upon the reflection of sound from any surface. Now as you can see, for echo to happen, the sound must travel to this distance and then come back to the listener. So whatever is the distance between the person and the obstacle, the sound has to cover twice that distance. And say it takes a time t for sound to cover this distance, then the velocity of sound is equal to twice this distance divided by the time it takes. Alright. Fine. Initially the distance is d, but that is the one-way distance. But when you are emitting the sound, it is going and reaching the obstacle, getting reflected there and coming back to your ears. So it's basically covering twice the distance between you and the obstacle. Hence 2d divided by the time it takes. That's the velocity of sound. Alright. So from here, from this formula, what can we find out? We already know that for echo to happen, time should be at least 0.1 second. And the velocity of sound in air is 340 meters per second. If you plug in these values here, you will find out the distance turns out to be 17.0 meters. This is the minimum distance that should exist between you and the reflector or the obstacle, whatever you call it, for echo to happen. So whenever you are emitting any sound, for echo to happen in air, the minimum distance between you and the obstacle should be 17 meters. It can be greater than this, but it cannot be less than 17 meters. If the distance is less than 17 meters, echo won't be produced, because then your original sound and this reflected sound, which we are calling as echo, will enter our ear within 0.1 second and we will not be able to distinguish it as two separate sounds. But as I said, this is only for air, because if you go in water the velocity of sound is equal to 1420 or I think 70, I'm not sure about this, just check it, 1470 meters per second. So because of that reason, the value of V changes, so the value of distance will also change in water. In water it is an even greater distance. But the fun fact about this is, the really interesting area is that when now we found out the distance, the minimum distance which is required for echo to happen, and that is the velocity of sound which we know in air into time divided by 2, because velocity is 2 times distance by time. Therefore the distance was found out by this formula, Vt by 2. Now the fun part is, if you are trying to measure what is the speed of sound experimentally, you can also do that using this formula. Say you are standing here and in front of you there is a tall building, and you know what is the distance between you and building. Suppose it's 100 meters, much greater than 17 meters. So now you know the distance. So what will be V? V will be d into 2 by time. So you have a stopwatch, you produce a loud enough sound, it goes, reflects off the building and comes back to you. You know the distance and you measure with your stopwatch how much time it takes for the sound to come back to you. From there you can find out what is the velocity of sound in air. So just like you used the velocity of sound to find out the distance, if you know the distance previously, you can use that to experimentally check for yourself what's the value of sound in air, the speed of sound. Now there are certain conditions that must be fulfilled for echo to take place. For echo to occur, number 1, distance between source of sound and obstacle should be at least 17 meters in air. Alright, at least an air are keywords. Why at least is keyword? Because it can be greater than 70 meters. And air is a keyword because in different mediums this distance is different. Number 2, the original sound produced by the source should be loud enough and must have sufficient intensity. So the sound that you are producing, it should have that sufficient intensity to go hit an obstacle and then come back and still be audible to you. You cannot produce a sound which is very feeble. You just can whisper something and expect it to hit a hill which is 100 meters away and then produce an echo. You have to be loud and clear. The sound should be intense enough. And finally, number 3, the size of the obstacle should be greater than or equal to the wavelength of sound. So the sound that you are producing, now see, we don't exactly have a control over wavelength. What we can control is our frequency by modulating the pitch in our throat. And we know velocity is frequency times lambda. So if you modulate frequency, we can in turn modulate lambda indirectly. And therefore, you should keep in mind that this wavelength should be, or rather the size of obstacle should be of the same order as the wavelength of sound. So if the wavelength of sound is like this, the obstacle should also be of a similar dimension as that of the wave, so that it faces an obstacle and then returns back. If suppose I am sending a sound which has a wavelength like this, and here I place a small obstacle, what will happen is the wave will simply bypass the obstacle. So the dimensions of the obstacle should be comparable to that of the wavelength of light, in this case that of sound, so that the echo happens. So you have to keep in mind these are the 3 conditions for echo to take place. First of all, since our persistence of hearing is 0.1 second, the distance between source of sound and obstacle in air should be at least 70 meters. Secondly, the original sound should be loud and intense enough so that it hits an obstacle and still when it comes back it is audible. Finally, the size of obstacle should be of similar or greater dimensions than that of the wavelength. Otherwise, as I said, it will bypass the obstacle simply. So these are the conditions that must be fulfilled for echo to take place in air. Now, can we human beings hear sounds of all frequencies? Well, no. We have something which is known as the range of audibility. We can only hear sounds which lie in a certain frequency range. We can hear sounds which lie between 20 Hz to 20,000 Hz. But well, let me say this is just a theoretical limit. Most of us, we cannot hear sounds which are such low in frequency and such high in frequency. Our audibility range generally lies between somewhere 40 to 7,000 Hz. This is the average sound range that we can hear because we live in urban areas. At all the times we are exposed to a lot of noise pollution, whether it is the honking of cars and vehicles, whether it is the normal sound of the household like the refrigerator, television, fan which are on, or maybe it is the noise pollution created by the various loudspeakers, mics in different areas. As a result of that, and as a result of continuous exposure to that, our range of audibility decreases. But theoretically, humans can hear between 20 and 20,000 Hz. You cannot hear sounds which have a frequency greater than 20,000 Hz and less than 20 Hz. The sounds which are less than 20 Hz, those are called infrasonic sound, and the sounds which are greater than 20,000 Hz are called ultrasonic sounds. And this is the range where we can hear. This is known as I said, the range of audibility, obviously, of human ear. For different other animals and species, the range of audibility varies. As take the example of dolphins. Dolphins and bats, they can hear ultrasonic sound. Bats can hear sound up to 100 kilohertz. On the other hand, for infrasonic, take the example of dogs and elephants. They can hear infrasonic sounds. So it's only for the human ears that this is the range of audibility. So if you are asked that what do you mean by range of audibility? Well, it is basically the range of frequencies, 20 Hz to 20,000 Hz, to which the human ear is sensitive or audible. Now, where are these applications for these things that we studied just now? The main applications of this sound is in the area of two techniques rather. One of them is called echo-depth sounding. The other technique is called sound ranging. What are these? Well, what is echo-depth sounding? Echo-depth sounding, you must have heard the name of this instrument, sonar. What does sonar stands for? Sound, navigation and ranging. So sonar is basically like this. If you have a ship, sonar is an instrument on that ship, and say you are traveling in oceans and you want to know what is the depth of ocean bed at this place. What is this depth? So what does this sonar do? Sonar sends a wave. What kind of wave? Ultrasonic wave. It sends an ultrasonic wave, and at that moment it starts recording the time. The ultrasonic wave goes down and hits the bed of the sea or the ocean and comes back to the ship, to this instrument, that is the sonar. Now the sonar, it already knows what is the speed of sound in water, what is the speed, and it is measuring the time that it takes for this journey. So from here it can find out the distance. We know the velocity is 2 times distance by time, therefore velocity into time by 2 is the distance. By using this formula it can find out what is the depth of the seabed. We have to divide it by 2 because it's a to and fro journey. It is covering the same distance twice. This is the principle in which sonar works, and this kind of technique is called echo-depth sounding. When a fisherman is trying to catch fish, he uses the same technique. He takes a ship or a trawler onto a sea, and a large shoal of fish is located here. Shoal of fish is located here. Sends down the signal from the sonar. Because of this large shoal, the signal gets blocked here. It's reflected back. By knowing the distance, it can get an idea where the shoal of fish is located and thus catch it. And another technique that we have is the technique of sound ranging. What is the technique of sound ranging? This is something that bats or dolphins use to locate their prey. Suppose bats travel at night, and if you have ever seen one in real life, you will find out that they travel tremendously fast. So how do they travel so fast and yet not get hit by an obstacle? Even if a bat comes pretty close to you, at the last moment it will get deflect away and go properly. So how does it manage to do this? So if this is a bat, suppose, and it's traveling very fast, and here is an obstacle, what the bat does is at every moment it emits this kind of ultrasonic waves, and the ultrasonic waves hits the obstacle and comes back to the bat. From here it can calculate how much time it takes for the waves to come back, and therefore from that it can calculate what is the distance. But obviously bats do not do this mathematics to calculate the distance. They know how to do this just as we know how to sense different tests, or how to sense if there is something hot or cold on our skin. These are the senses which we develop right from our birth. Same is the case for the bats. It is ingrained in their senses, but it is by this scientific method that they can get to know how far the obstacle is, and swiftly avoid it. Same is the case of dolphins. Dolphins, when they are inside the seas and oceans, they send this kind of ultrasonic waves towards shoal of fish. It gets blocked there, reflects back, calculates how much time takes place for this reflection to occur. From there, it can find out where the shoal is located and thus catch its prey. Another related area of sonar is radar. Radar stands for radio detection and ranging. DAR stands for detection and ranging. This is navigation and ranging. SO is sound, RA is radio. The only difference between sonar and radar is radar uses radio waves while sonar uses ultrasonic waves. Now ultrasonic waves has the same speed as sound, which is 340 meters per second, but radio waves, they have the speed of light, 3 into 10 to the power 8 meter per second. Because of this reason, radars are incredibly fast, and radars are used for all kind of radio communications, even with the satellites that are constantly in orbit around our Earth. But radar works on kind of the same principle. Finally, where do these ultrasonic waves find one application? Well, we are familiar with this. One of our family members might have done this once in their lifetime. It is called ultrasonography, or in short USG. Doctors usually recommend this USG test when they want to find out the functionality of your abdomen region generally. So this USG ultrasonography also uses the technique of this ultrasonic wave, sending it into your body, calculating how much time it takes to come back, and from that it can do a mapping and imaging of your internal organs. In the next class, we shall solve certain numericals based on this topic of echo, and probably move on to the next area of forced vibrations and natural vibrations.